Okay. Thank you to the organizers for inviting me. Thank all of you for joining. Uh, this is not really a QCD talk. It's not a gravity talk, but it's about integrals and cuts and such. And I hope it will be of interest for all of you anyway. This is a working collaboration with Jake, Hofi, Andrew, and Matt. And it's based on this preprint. So what's the big question here is what we're trying to do is try to understand the singularities of scattering amplitudes. Or if you don't, if you're focused on a single integral, you can try to understand the singularities of a single given integral. And we know we have a pretty good idea of the simplest singularities you can have, and these are branch cuts in a given channel, right? So you have things like Sijk for some external momenta, Pi, Pj, Pk, and they have a branch point starting at the threshold. So these are the simplest singularities that arise, but there's of course more than that. And of course, we're trying to understand what they are. And one of the tools we can try to use is causality. How does causality constrain singularities? And of course, in this connection, the Steinmann relations make an appearance, right? And the Steinmann relations I will review in a minute are telling us about relations between sequential cuts, and they're very much tied to causality. The other complication here is that if we go beyond these simple singularities that I mentioned at the first bullet point here, we have singularities that can appear on non-physical sheets, right? So roughly what they are singularities that happen for kinematics that's not real and not physical. And of course, because of this, they're a bit harder to understand. So that's another question that we'll have to face. So what I will try to do is to provide some mathematical tools to help answer these questions. And what I will say is very general, should apply for many integrals, including non-planar, but I will restrict to polylogarithmic integrals for now. I think it should be possible to go further, but that's for the future. Right, so sequential cuts. So this is a story that goes back a long way. I put a number of references here, which is a very incomplete list. There's been a lot of work done already a long time ago, and of course, recently there's been a resurgence of this research. So roughly what these relations tell you is that cuts of a connected S matrix element in overlapping channels vanish. And there's a caveat here I mentioned in a footnote, but I will explain it on the next slide. So there's a number of questions you may have here. For example, do Steinmann relations apply integral by integral, or is there some conspiracy in the sum that makes these relations work? The other question is that you have to define precisely what we mean by sequential cuts, and this is a bit of a tricky question that I will describe how to solve. And doing this, I will describe how to connect to more recent mathematical literature. By recent, I really mean maybe 70s or 90s. I mean, we're really catching up to some of the things that people have done a long time ago in the mathematical literature. And then, of course, you would want to use the answers that you obtain in this way for doing bootstrap. This is, again, something that we are pursuing. Right, so let me describe in a bit more detail what I mean by Steinmann relations. So here I have, I hope you can see my pointer. I took two cuts, and you can look at some quantity. This is an S matrix element above and below the cut and above and below the other cut. So you can really define four quantities, S plus plus, plus minus, minus plus, and minus minus. And the way Stapp defines this, he keeps the momenta real and complexifies the energy. And then he defines the above and below the cut in terms of the imaginary part of sums of energies in a given channel, right? So it's defined like here. The sign of the inequality corresponds to the plus and minus there. So the discontinuity is just the difference between the value of this function above and below the cut. And then, of course, the sequential discontinuity is defined by taking the difference between the discontinuity on the first side and discontinuity on the second side. So you take this difference and you subtract this difference out of it. Now, this is an example of this one-loop triangle integral, and I'm giving it here. I'm giving the explicit form of this integral, just to emphasize that if you try to apply this recipe to it, it's very unpleasant. I mean, you have the arguments of the polylogarithms are defined in terms of these ratios of momenta. And of course, if you try to put energies in here and make them complex and take positive, negative, imaginary parts, it's a mess. So that's clearly not what you want to do. What people who are doing bootstrap using this approach of Steinmann relations, what they do is they use the symbol or they use the iterated integral representation. So just a very quick reminder or introduction. An iterated integral is just an integral along a path, and along the path you arrange a number of differential forms that you're integrating, and you're integrating them in a sequence. So you end with the first, and then you start integrating the second, and then the third, until the last one. And it's often very useful. This is just one term. You can have multiple terms. And it's often very useful to sort of forget some of the details here, forget the details about the path of integration, and you only keep the endpoint. And that's the symbol. And of course, this is an operation that loses information when you do it. And here you can take a discontinuity, which at the level of the symbol, what it means, you have a function such that when you divide it by 2 pi I and you take the symbol, it just corresponds to chopping off the first entry if you take the discontinuity along a branch cut that vanishes, that has a branch point where this entry here vanishes. So this is, I denoted this with a lowercase d because the connection to this uppercase d is not really completely obvious at this point. Now, in terms of the iterated integrals, one of the nice features that they have is that you can really do an analytic continuation. So you can start, you can have any path here, you integrate some differential forms, and you get the value of the function outside of a convergence region, say, of a power series, right? So this integral is better for analytic continuation than a power series expansion. And here I have a very simple example. You can take this integral for the logarithm, and we can take it along 2 different paths, and of course you get a factor of 2 pi I as you go along the path, and then the inverse of the second path. And this is, of course, we know This is a familiar phenomenon for all of us. It's just the fact that the logarithm is multi-valued. So for the monodromy approach, we're using the iterated integral to define an analytic continuation of the function, just like for the logarithm. And we do this by appending to the integration path some other paths that go around poles in the differentials that appear in this iterated integral form. And doing this allows you to go to other sheets in a physics language. And this was, of course, studied in a lot of mathematical papers. They're not so easy to read. I learned about it from Zhangqiang Zhao's lectures that I found a bit more accessible if you want to learn more about this. So I will define this discontinuity with lowercase d as just the difference between the value of the function and the value of the function after you analytically continue it by this monodromy operator. And this definition satisfies this symbol constraint that I imposed here. I think I want to skip this slide. Now, the discontinuities, if you compute them with a Kutkowski rule, the real structure plays a crucial role, right? So you have to replace the cut propagators by these delta plus, right? So of course you don't really know how to do that if the kinematic point is complex. And so of course the real structure plays a crucial role in the computation of the cuts. Up to a sign that's maybe not so essential at this point, I don't think I have time to describe it. The discontinuity computed from monodromy is equal to the discontinuity computed with the approach of complexified energy whenever this second one is defined. Now, there's of course then there's a natural question: what happens if you take two monodromies around two different branch points, right? So I have some singularity loci F1 and F2, and they have overlapping cuts. And then I consider two different paths, gamma 1 that goes around the locus F1 equals 0, and gamma 2 that goes around the locus F2 equals 0. And then the Steinmann relation, I could write it I just replace the discontinuity by this monodromy along the second path and then along the first path. And then I say this is 0. Now, a priori, this product, gamma 1, gamma 2, or gamma 2, gamma 1, it can depend on the order, right? So I will have some more comments about this soon. But first, how do we compute these monodromies? So in fact, this is not very hard, and the people who've thought about polylogs, they should kind of find this discussion familiar. You start taking total differentials. So suppose you want to compute the monodromy of Li2, right? And you start taking total differentials, and you obtain lower transcendentality functions. And then you can write these equations in a first order form. So you put these functions in a vector, and you introduce a matrix which has some differential forms here, omega 1, omega 0, which are defined like so. So this, starting with Li2, we obtain a matrix of whose entries are differential forms. And this matrix, of course, has some very special properties. So it's closed, and it's flat, right? So this is a connection which is flat. And the fact that it's flat, this is related to what's known as integrability of the symbol for people who know this language. Now, if I take this, so this connection will be one of the central objects for me in the following. Now, if I put all of the solutions of the linear system in a matrix, so in other words, I take the path ordered exponential of this matrix with some starting point. The starting point is not very important right now. I obtain what's called a variation matrix. So instead of the dilogarithm that I was interested in, I get a whole matrix of things, which is actually upper diagonal or upper block diagonal in general. In this case, it's just upper diagonal. There's one subtlety here, which has to do with the divergences that may appear. And these divergences are regularized by what's called tangent base point regularization. This basically corresponds to putting a small cutoff and removing all the logarithmically divergent integrals. More formally, what it corresponds to is choosing a parametrization for the path where the tangent vector at the origin, at the beginning of the path, is a unit vector.
By the way, 5-minute warning.
Yes. So this is an example, right? So we know that for the dilogarithm, there's two branch points, one at 0 and one at 1. So we can compute the monodromy around 0, and it actually corresponds to a left multiplication by some matrix M0, or a monodromy around z equals 1, and that corresponds to a right multiplication by matrix M1. And this is the explicit form of these matrices. And you see that they're very simple. They have just, I think there should be 1 here. I forgot a 1 in the last row. So they only have 2 pi i's or powers of 2 pi i's and 1s. And so they're very simple matrices. And in this case, they don't commute. You can check this. It's a very simple calculation. So, right. Here I have a very quick comment that in principle, if you have this connection omega, you can, the whole ambiguity of the function that this defines is encoded in the starting point, the choice of the starting point. So if you know the value of your integral or your amplitude or whatever you're computing at a given point, then you can start your integration from there. And basically this takes care of all these beyond the symbol ambiguities. Okay. So there's an interesting tension between the commutativity of this disk with capital D and the monodromy, and this is in a sense what you need to remember is that the discontinuities that are computed in the first approach are along paths that are very restricted, whereas in the monodromy approach, we really allow the paths to go wander off to other sheets and then come back, and they can do many more complicated things. I don't want to finish before giving you a few examples. So this is we computed for the one loop, just to give you one loop example. This is the one loop connection for the triangle or the box. These are all functions of z and z bar that I defined on one of the first slides. And this is the exponential. There are 4 monodromy matrices going around 0, 1 for z and z bar. And this is their explicit form for z. Then I can show you a 2-loop example, which is, of course, much more complicated. This is the connection for the box triangle integral. And I don't think I have the, yeah, I don't have the explicit form of the monodromy matrices here, but they would be kind of similar to this one. So it would be factors of 2 pi and so on. Now, this connection has an interesting block structure. And really, there's a lot of information in these dimensions of these blocks, and it's connected to Hodge structures and weight filtrations and so on, if you care about these things. Now, perhaps a more physically motivated formula, if you have a two-loop triangle box integral or a double box integral, you know you can only take a limited number of cuts, of iterated cuts. And that's encoded in these formulas here, right? So if you try to take 3 cuts in the say the S channel, if you put your integral horizontally, then you get 0. Or if you try to take 2 cuts vertically, you get 0. Okay, I'm out of time. Basically, what we want to do is to take this technology and apply it in reverse, right? So we don't want to, here we kind of start with the answer and we understand the structure, but we would like to go the other way. So that's the basic idea. We'd like to go from physics to constraints on this connection, such that it would be determined completely or as much as possible. And of course, the promise here is that if we understand the S matrix on all of the sheets, including the complex singularities, that could unlock some more potential for our understanding. Okay, thank you.
Let's all thank Cristian for the talk. And we can open it up to questions. So you can either raise your hand in the participant zone or just speak up if you have a question. Enrico has a question. You can go ahead.
Hey, Cristian. Thanks for this nice talk. Can you say maybe a little more of what you envision for bootstraps besides the type of like adjacent letter constraints that you can, well, in at least planar n equals 4 people have imposed already?
Well, so really, the idea would be that it should be possible to obtain a complete understanding of all the singularities. Just if you think about I'm trying to carefully phrase this without, it's related in some work in progress. But so I don't think I'm going to be able to give you a satisfactory answer without revealing too much of what we're thinking about, and it might be premature. But let me just say that we have some very concrete ideas that look promising. And so it should just be possible somehow to use physical principles to constrain this connection. And we already know some of them, right? The first entry condition, we just tell you that you have to have this kind of things here, right? And then the second entry conditions would be, okay, what kind of things are you allowed to have? What kind of cuts are you allowed to have that follow after this, right? And Steinman already tells you some of this, but not completely, right? So you need to go a little bit further, and you can, it seems like, but this is for some future work.
All right, thanks. I didn't want to push you.
Isn't it also true that Steinman wants a mass gap, and we don't have any mass gap in?
That's true. That's a good point.
4, and so it's not completely obvious how to do it. And I don't think your first paper completely addressed this situation. So
that's right. That's a very good point. The massless case, I mean, in general, a lot of this, actually, maybe all of this early literature and the S matrix kind of completely ignored the massless case, and it was for good reasons. But I think now since we understand a little bit more, perhaps we can be optimistic that we can go a little bit beyond what they did.
Let's see. We're running a little short on time, but Atul, maybe if you have a quick question.
Nice talk, thanks. If it's possible, could you explain again how Steinman relations are related to causality? I'm trying to learn this subject. I just wanted a basic explanation if you can give me.
It's not something that can be done in a minute, I'm afraid.
Sure, that's okay.